Hi, and welcome to another lesson in the physics video series. Today we're going to be discussing the inelastic collision, which conserves momentum but not kinetic energy. We've mentioned this several times in the past videos, but today we're going to spend an entire video just proving it. Alright, let's get started. I've selected this particular problem for you. It says, base your answer to the question on the information and diagram. A 1,000-kilogram empty cart moving at a speed of 6 meters per second is about to collide with a stationary loaded cart having a total of 5,000 kilograms as shown. After the collision, the carts lock together and they move away. This is another case of a two-body problem where a light car hits a heavy car. The question simply asks, how does the kinetic energy of the combined carts after the collision compare to the kinetic energy of the carts before the collision? And so we've been saying that the kinetic energy of the combined carts after the collision is less than the kinetic energy of the carts before the collision. But we never have really proven this, but we've given intuitive hints. We know that after these two collide together and move away, they move away at a slower speed. That loss of speed is really the loss of kinetic energy. However, we have not taken any time to prove it. So let's first look at a simple proof. We know that the momentum before and the momentum after have to be the same. But for energy to be conserved, kinetic energy before and kinetic energy after must also be the same. Well, here we have this equation, kinetic energy before, question mark, equals kinetic energy after. So we're asking if the energy before will be equal to the energy after. If they are equal, then of course we will have conservation. However, we can't come to a conclusion unless we first set up the equation. So we start with this. The kinetic energy formula is equal to 1/2 mv squared. Since there are two masses, each mass gets its own equation. Mass 1 has its equation. Mass 2 will have its equation. There'll be a before equation, there'll be an after equation. 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. So this equation will now be filled in with the variables that we have. We know that the v2 is 0. The kinetic energy of the first car is 1/2 times 1,000 kilograms times 6 meters per second squared. So that gives us 18,000 joules. This amount of energy has to be the same amount after the collision if it is to be conserved. If we get a different value, and it'll only be equal or less. You'll never have more energy than you started with unless you add it to the system. So if we calculate the after kinetic energy and it's the same value as 18,000 joules, then we can say yes, it was conserved. But if we get a lower value, then it was not conserved. We already know that the after collision speed is much less than the before collision speed. So you can already see that energy has been lost. If you recall from the conservation of momentum expression, Vf equals this mass ratio as a fraction of the original speed, you can see here that the original 1,000 kilograms plus the 1,000 kilograms plus the 5,000 kilograms of the second mass, that factors to a 1/6 fraction of the original speed. So automatically, your final velocity is 1/6 of whatever the original impact velocity of mass 1 was. So that turns out to be 1/6 of 6 meters per second, which is equal to 1 meter per second. If you take this 1 meter per second and you put it in the KE after formula, 1/2 m v final squared, the mass here is the combined mass of 6,000 kilograms. That's the two cars locked together. 1/2 of 6,000 times 1 meter per second squared. That only gives you 3,000 joules. So you can see that the energy before the collision was 18,000 joules, and the energy after the collision was 3,000 joules. Where did that energy go? It probably got lost in the form of heat, light, and sound. Whenever there's an impact, there is heat given off. Just like if you rubbed your hands together, they would get hot. Any light that might be given off would be in the form of, say, sparks when two pieces of metal strike each other. And any sound, of course, would be the crashing together of the two masses. And of course, heat, light, and sound are the most common energy losses that you can measure. So for the inelastic collision, we have just done a simple numerical proof that KE before does not equal KE after. The KE before is always greater than the KE after because the two-body collision, once locked together, loses velocity, then heat, light, and sound. That's where the energy leaks out of the system. Let's take a look at a more rigorous proof. In this case, I'm going to set up the conservation of momentum expression for two masses, M1 and M2. I have them boxed out as red and blue. It should be no surprise if you've watched the previous videos that the momentum before equals the momentum after, and that you can find the final speed of the group by using the simple conservation formula. We know that we can set the momentum before equal to the momentum after, cancel out the stationary vehicle, factor out the common speed V1 prime equals V2 prime equals V final, and we come to this conclusion that the final speed of the group after the collision is equal to Vf equals a mass ratio of V1. That's the general expression for the final speed of the group after the inelastic collision. This result has been developed numerous times in previous videos. For an inelastic collision, we say that momentum is conserved, and that means that the momentum value before the collision has to equal the momentum value after the collision. Let's take a quick example of when the two masses are equal. If the two masses are equal, m1 equals m2, and then the final speed is a mass ratio of the initial v1. m1 divided by m1 plus m2, but m2 is equal to m1, so this is another m1 here. We get 1/2 v1. So the momentum before the collision was just m1 v1 because the v2 was 0, and then the momentum after the collision, here we have this expression, it's the combined masses times their final speed. And we know that their final speed, Vf, is equal to 1/2 of the original speed, V1. When we simplify this, we get m1 plus m2, and m2 was the same as m1. m1 plus m1 times a half, v1. 2m1 times a half. The 2 and the half cancel, leaving you with m1 v1. And here's a general solution that proves that the momentum before, which was m1 v1, is equal to the momentum after, which is m1 v1. That is the proof of the conservation of momentum. And then the next question is the kinetic energy conserved? And we already said no, and let's see a more rigorous proof below. We ask the question, does kinetic energy before equal kinetic energy after? So we have to set up a kinetic energy equation for each mass on both sides of the dashed line. The dashed line represents the point in time to the left before the collision, to the right after the collision. The kinetic energy formula is 1/2 mv squared as a general expression. So now we create an expression for each one of the boxes. There'll be a red and a blue on the left, a red and the blue on the right. 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 prime squared. Remember, the prime means after. 1/2 m2 v2 prime squared. On the left side, we know that the v2 was at rest when it got crashed into by the mass 1. So the v2 cancels out and this term is gone. So the remaining term on the left side is 1/2 m1 v1 squared. That is the kinetic energy before the collision. Whatever this mass was, times whatever speed it was going, that is the kinetic energy that should be equal on the right side after the collision if there was conservation of kinetic energy. But there isn't. We already know that once they hit together, it moved away at a fraction of the speed. Let's continue our derivation. We're going to spend our time looking at the right side of this equation and seeing if the answer we get from this derivation matches 1/2 m1 v1 squared. So over here on the right side, we know that v1 prime and v2 prime are both vf, and make that replacement. We know that the two masses lock together, so you have a total expression of 1/2 m1 plus m2 vf squared. And we recall from the previous momentum expression that vf is equal to its own fraction ratio of masses times v1. So I put that in here and I square the whole thing because vf is squared, and then I cancel and simplify. And that leaves me with an expression that reduces to Ke after equals 1/2, and now parenthesis, here's a new mass ratio. It's different from the one for the momentum conservation. m1 squared divided by m1 plus m2 times v1 squared. Let's test this expression with the sample problem we started doing where the two masses were equal. If m1 equaled m2, and we know that the final velocity was actually only half of the original speed, let's insert the masses into this new ratio and solve. m1 squared divided by m1 plus m2, and m2 is m1. And when we go through the factor here, and m1 cancels with one of the squareds, leaving with a fraction of a half. So we have 1/2 times this new fraction, 1/2 m1 v1 squared. And this 1/2 m1 v1 squared, that is the same as the kinetic energy before. This expression is the Ke before. So you could see that the Ke after is actually only half of the Ke before. That's when the masses were equal. So we can conclude that the kinetic energy after the inelastic collision is always less than it was before the collision. There's no conservation because there's a loss of kinetic energy, and it comes out in the forms of heat, light, sound, and reduced velocity. In closing, let's apply the rigorous proof to the 5-to-1 ratio, which is the problem we started at the very beginning of this video. Light hits heavy. Mass 2 equals 5m1. And if you recall that the final velocity of the group as it moved away together, 1/6 of the original speed. Here is our general solution for Ke after. It equals 1/2 of a mass ratio times v1 squared. So we know that 1/2 times m1 squared over m1 plus 5m1, because remember, m2 equals 5m1. And when we simplify that, we get 1/2 of 1/6 m1 v1 squared. We're going to rearrange that, and we're going to take the 1/6 out and put it in front, and we're going to leave the 1/2 m1 v1 squared inside the parentheses. The 1/2 m1 v1 squared, that is the Ke before. So we're dealing with a Ke after that's 1/6 of the original Ke before. Ke after equals 1/6 of the original kinetic energy before. Ke before clearly does not equal Ke after, and so you do not have conservation. Let's take a look at an alternative proof. We know that the Ke after is equal to 1/2 of the combined masses times the final speed of the carts moving away together squared. When we replace the ratios, m2 was equal to 5m1, and the Vf was equal to 1/6 v1, which we got from the conservation of momentum formula, reduce and simplify, and we get the same result above, which was 1/6 of parenthesis 1/2 m1 v1 squared close parenthesis. Inside the parenthesis is Ke before. So either way, we get the same results. This was a very developed proof for something we've been saying for a long time, that in an inelastic collision, momentum is conserved, but not kinetic energy. I hope you enjoyed this video, and I thank you for watching. We'll see you in the next video.